I would want to welcome you all to our 15th Leonards lecture and the 15th Purdue Technical Society workshop that just concluded. I want to just briefly acknowledge our sponsors whose loyal support makes this event materialize every year. And I want to offer a special thanks to Professor Leonard's son, David, and his wife, Rebecca, who will honor us with their presence every year. So welcome once again back to Purdue. So welcome to the 15th Leonards lecture, which is going to be offered in just a few minutes by Professor Patricia, Trish, to many of us, Culligan, Robert and Christine Carlton, Professor of Civil Engineering at Columbia University. We're delighted to have you here. The lectures, as many of you know, honors the memory and the legacy of Professor Leonards, a giant in our field who put Purdue on the geotechnical world map many years ago. And as in previous years, the theme, the lectures serves as the highlight and the bookend to the Purdue Geotechnical Society workshop. And the theme of the workshop is generally chosen to complement the lecture. And over the years, the theme of the workshop has covered a lot of ground, if you allow me that pun. And in some cases, like in our energy geotechnics workshop that we had a few years ago, essentially addressing topics that have, if you will, a reach that goes beyond that of a traditional geotechnical engineering, or certainly beyond our field. Even more so today, as we, inspired by Professor Culligan's talk, we address a topic that has enormous significance, not only for our profession, but for society as a whole. We see this as an opportunity to reflect on some of the challenges and some of the future and the role that our profession can have in addressing some of the challenges that lay ahead for our society. But also, if you will, as an opportunity to remind ourselves, in the words of Neil deGrasse Tyson, that science and engineering, I will add, can and should always be in the service of civilization. Not out of planning, but purely out of serendipity, our program today falls during Earth Week, which, as was pointed out, with Earth Day coming tomorrow. And so how fitting that this happened to be the case. Before passing the word on to Professor Culligan, I would like to say something about our speaker's background. Trish is a graduate of Leeds University and Cambridge University in England, where she received her PhD. After an extended postdoc at one of the premier institutions in our field, the University of Western Australia in Perth, she joined the faculty first at MIT and then at Columbia University, where she is a chaired professor. She serves as the founding associate director of Columbia University Data Science Institute and the co-director of the Earth Institute's Urban Design Lab. Her expertise is in the field of geoenvironmental engineering, and what stands out from the review of her research portfolio is the incredible range of her work with research in physical modeling of transport processes, nanofluidics, unsaturated soil mechanics, ecoinformatics, measurement and prediction of urban and rural hydrological processes, performance of green infrastructure, coastal resilience, and more. This range is the result of an incredibly curious mind, of someone who sees the intersections and connections before other people do. Not in my words, but a bit restating what Professor Mark Randolph, who interacted with her closely during his postdoc at the University of Western Australia, once told me, several years after she had left the Western Australia, drawing attention to really the unique creativity and ability to envision big ideas that Trish brought to the table as a young researcher, already as a young researcher back then. Professor Culligan is a colleague of many interests, and amongst other things, she's a fluent French speaker with a degree in language, literature, and from the University of, from a French university. An avid skier, a passion that she and I share. She's a woman of incredible energy. I recall shortly after she joined MIT, while she was in the process of setting up her lab, developing her course, hiring new graduate students, that she took the time to develop a freshman seminar course for MIT freshmen on the impact across European countries of the adoption of a unified currency. And I was like, wow, okay. And she always had something new going. I have known Trish for many years. I was in the audience as a graduate student when she presented her interview seminar when she first came to MIT. I was a student in her first graduate course taught at MIT, and we even worked together for a very short period of time as part of an effort to redesign, in my very last semester, to redesign MIT's civil engineering curriculum. She also trained, holds the distinction, I would say, of having clarified to my generation of MIT graduate students, of both foreign and native, the distinction in the use of the words which and that, and the strong of her formal British education in the written English. If I had sparked some doubts, you may want to talk to Trish over dinner about this. More seriously, Trish has been a generous friend, a mentor, always available to listen and provide advice. The integrity, the kindness, and the grace with which she has conducted herself and often navigated sometimes rough waters of academia have and continue to be an inspiration for me. So Trish, welcome to the please join me in welcoming the 15th Leonards Lecturer, Professor Trish Cully.
Marika, thank you very much. I barely recognize myself. I'd also like to thank the Purdue Geotechnical Society and more specifically the organizers of this workshop. It's been an amazing day. I'm honored to be here, and I'm very grateful to have the opportunity to present the 15th GA Leonards Lecture. I wanted, before I started the lecture, to give you some insight into my own personal career, because I think it might frame some of the material that follows. As Marika said, my own expertise lies in the field of geoenvironmental engineering with a focus on porous media flow and transport. I started my research career looking at the subsurface disposal of both high-level and low-level nuclear waste, and continued in that direction to expand more broadly into issues that related to groundwater flow, contaminant transport, and remediation. But when I moved to New York City in 2003, I became more and more interested in issues that relate to the challenges of urban sustainability, and specifically what our profession, those of us who have training in geotechnical and geoenvironmental engineering, can bring to the table when it comes to addressing some of these complex challenges. If you look at some of the projections that the United Nations are providing for urban areas around the planet, within a very short time, 1 to 2 decades from now, we might expect about 70% of the world's population to be living in cities. So the sustainability and resilience of these areas is important to the livelihood of billions of people around our planet. And when we look at some of the pressing needs, when we think about urban sustainability and resilience, climate change actually rises pretty close to the top. So that actually speaks to my personal interest in climate change and the impacts and challenges that it poses for our particular field. So I've got an overview of what I would like to go through. in the next 40 to 50 minutes. I'm going to give some introduction to climate change. We've seen this before in some of the prior presentations today. Call out some of the challenges, some of the impacts, and some of the research needs. Some of these will be general, and some of these will be a little bit more specific to our profession of geotechnical engineering. I'm then going to talk briefly about a climate adaptation study that I've been engaged in myself with multiple other researchers, with city government agencies, with many of my students, and with some professional collaborators. And that involves New York City's green infrastructure program. I then move on to what I see as an adaptation strategy that's rising more and more to the fore, and that's a shift from reliance on centralized infrastructure systems to more decentralized and neighborhood level infrastructure systems. And I'll talk about that also more generally, but also more specifically about what it might mean when it comes to geotechnical engineering research and practice. Then I just have one slide on future needs, because I think the future needs in this area are quite enormous, and it's up to us as a community to come together and think about them collaboratively. So let me start with the climate change impacts. I've got two graphs up here which come from the EPA website. There are many different resources that we can access when it comes to thinking about global impacts. And I'm just displaying the global sea level rise and temperature rise projections that are the result of multiple climate change models, with the lower rises in terms of sea level around about 1/2 foot being associated with low emission scenarios, and the higher rises, which are getting above 6 foot, being associated with larger emission scenarios. And as we're all quite aware, the uncertainty in these predictions is pretty huge, which makes it quite difficult for us to know as engineers how to address some of these projected impacts. And if we look to the right, we have the projected impacts for temperature rise. And again, we'll see that there are multiple scenarios on the table depending on what type of emissions we're going to be seeing in the future. But the temperature rises also span from about 1/2 degree to 8 degrees Fahrenheit. So we can be certain to some extent that on a global scale, we're going to see sea level rise and we're going to see temperature rises. But I would argue that for those of us in engineering practice, the global projections are not necessarily of much use because we design to specific local conditions. And also as geotechnical engineers, we know that the subsurface of the sea is not a bathtub. There are areas where we're still seeing deposition of sediments. There are areas under increased water height where we're going to be seeing different subsidence depending on the material that makes up the subsurface seabed itself. So we know that we are going to see global sea level rise, sea level rise that is going to vary in different places around the globe, and that is when we think about specific design challenges that we really want to look at. So I have some more projected images here that speak to what is expected or might happen in the States depending on the various emission scenarios. So on the left-hand side, we see some projected sea level rises. This is associated with a high emissions scenario, so this is quite an extreme sea level rise that tells us that on the eastern coast we might be expecting up to 5 foot of sea level rise. In the southern areas of the States, that might be higher in some locations. On the west coast, it might be lower in some locations. We also have on the right-hand side some of the projected temperature rises that are associated with the US. The top is the high emissions scenario. The bottom two graphs are the lower emissions scenarios. We can see significant temperature rises under the projected high emissions scenarios. And as was pointed out this morning, in general, one expects to see higher projected temperature rises in the middle of the US, lower projected temperature rises towards the coast. Now, if the temperature is going to rise, we are also going to expect changes in precipitation patterns. And these are something that as a geotechnical or geoenvironmental engineering profession is going to be quite important for us when we think of adaptation, design, and resilience. So these, again, are projections that are associated with high emission scenarios. They're shown for different seasons of the year. But we can see in general that we might expect higher precipitation than we're currently seeing in the northern parts of the US and lower precipitation in the southern parts of the US. But of course, this is going to vary by season. Finally, I want to put up something that I think is of great concern to me and is something that should be of concern to our profession. And these are some of the projections for ice melt in the Arctic as well as the Antarctic. And on the left-hand side, the two globes actually show the patterns for the ice sheet in the Arctic, the top being the existing pattern, and the two below being the patterns that are projected for towards the end of the century for different emission scenarios. And on the right, we're seeing what's happening with Antarctica. But according to my colleagues at Columbia University that study the Arctic, this summer may be the first summer that we actually see no Arctic ice. And if you believe the projections, we're moving towards scenarios where for most summers we're going to be seeing no Arctic ice. Now, there are opportunities associated with that, and people that are engaged in global trade, particularly shipping, might be quite excited about an Arctic ice passage that has disappeared and is now allowing better movement of shipping traffic between different continents. But for those of us in the geotechnical and geoenvironmental profession, we should be thinking about the impacts of reduced permafrost in this region and what that is going to mean to geotechnical structures that exist in this region and what that is going to mean to future development and how we're going to be taking this significant change into account. According to my colleagues at Columbia University that have been engaged in studying this problem for decades, they really do not understand what the disappearance of the sea ice is going to do to local climate in that area. So I think, again, this is something that our profession really needs to also be thinking about when it comes to how we need to imagine the type of challenges that are going to arise as a result of this. So I want to summarize here the climate change changes that our colleagues in climate science believe are ahead of us in the next few decades towards the end of this century, and also what those broad impacts are likely to be. So, as I said earlier, and as we heard throughout the workshop today, we do expect a rise in sea levels. We do expect an increase on average in global temperatures. We are going to see changes in patterns and amounts of precipitation in the northern areas of the US and in the region that I live in, New York City. We expect the precipitation to increase. But we also expect to see changes in the intensity of precipitation and changes in the dry weather periods between precipitation events. All of these are very important to us when we think about design and research. What has not been mentioned is that we also are going to see acidification of the oceans. This is going to be impacting the health of coral. We don't necessarily know what that's going to be meaning to storm surges, which will be on top of sea level rise when we think of impacts on coastal cities. We're going to see increased frequency and intensity and duration of extreme events. The Sandy event that hit New York City at the time was projected to be a 1 in 100 year return period event. That return period, we think, is going to decrease significantly as we move further into the century. And we're going to see changes in ecosystem characteristics. And as I mentioned in the previous slide, something that I think is going to be happening fairly rapidly is a decrease in snow cover and permafrost, which is associated also with a decrease in the sea ice, particularly in the Arctic region. So what are the likely impacts of this more broadly? All of these changes are going to impact our water resources. They're going to impact our infrastructure, probably in ways that we don't really understand at this point in time. The precipitation patterns are going to be quite disruptive to our food supply, and that is a big issue when we think of a planet whose global population is increasing and our ability to feed the people that live on our planet. We know ecosystems are going to change, and this is all going to be impacting human health and well-being. So these are all impacts that are important to the global population at large and important to those of us who are going to be living in cities, which is the majority of us in the next few decades. So with respect to the general research challenges that exist in this particular area, before we start thinking about issues that are more relevant to geotechnical and geoenvironmental engineering. In general, the degree of uncertainty in the climate change predictions and the climate change impacts does, as I mentioned initially, make it hard for those of us who are in fields that need to take action to understand what action we do need to take. So there does need to be an improvement in the global scenarios. But I think more importantly, an improvement in predicting what is happening locally. That is going to require not only downscaling of the global climate models, it's going to require, I think, increased instrumentation of local climate change, so that we can mesh the downscaling of the global climate models with on-the-ground data that will enable us to calibrate better what is happening at a local scale. This is less problematic for those of us that live in the US. We're blessed by an excellent number of climate monitoring stations, both those that are owned by our government and those that are in private research hands, such as my own, but available publicly. It's a much bigger challenge for many communities that are living in the global south and don't really have access to any meteorological data, so are unable to understand local climate variability, let alone the impacts that they might be facing as a community as larger scale impacts come forward. I think we need to develop adaptation strategies. This is important because we really cannot be certain about what the future is bringing, particularly at this point in time. So the strategies that we have to put in place right now to try and mitigate the impacts of climate change are going to have to be strategies that can evolve over time. The case study that I'm going to present is one such strategy. And it's not without its own challenges, it's not without its own uncertainties, and it's not without its own problems. When we think about trying to set the world on a pathway that doesn't take us to the extremes of sea level rise and temperature, we have to really think about achieving emissions reductions. And this, as was pointed out by a prior speaker this afternoon, is often referred to as a mitigation rather than an adaptation strategy, because we're really trying to mitigate the impacts of climate change. So we have to think about clean energy technologies. As was also mentioned this afternoon, we really have to start thinking about energy efficiency. Those of us in the States use a lot more energy than many of our counterparts in Europe. And clearly we use a lot more energy than many of our counterparts in southern areas of the world. So I think there's a lot to be gained for us collectively thinking about energy efficiency. We heard it today about CO2 storage options and the necessity for advancing research in that area. And I think we also need to think about measuring progress. So if we're serious about reducing CO2 emissions, we can certainly monitor those in the higher atmosphere to see what is happening at a global level, and that is important for the global climate change predictions. But I think we can also measure progress more locally. I would say maybe 5 or 6 years ago, Wade McGillis, who's a colleague of mine at Columbia University, installed the first CO2 sensor in the Central Park Met Station, which is one of the oldest Met stations in the country. So I think we need to start thinking more generally about how do we measure progress towards some of these important goals. And as was mentioned several times this afternoon, how do we communicate this? Not just within our own academic communities, but more broadly outside the walls of many of our universities. And not just to the general public. There are very many stakeholders involved in the decision making that needs to go on if we are going to move forward towards a future that is more sustainable and resilient. So with respect to geotechnical and geoenvironmental challenges, I think there are probably many people in the room that could come up with a more comprehensive list than this. I'm well aware of the challenges that are associated with rising and falling groundwater levels when it comes to groundwater contamination, remediation, and containment schemes. But when we think about rising and falling groundwater levels, which are going to be associated with increased precipitation events or decreased precipitation events, increased temperatures, which are going to change evapotranspiration. We also have to think about what that means to our underground structures and services. We have to think about what it means to our foundations, retaining walls and embankments, and we had some discussion about the retaining walls and embankments today. We also have to think about what that means to our groundwater resources themselves. There are many communities in the US whose sole water supply is groundwater. And if they are in regions of the US where we're seeing decreased precipitation events, their water supplies are going to be impacted by climate change. So there are many challenges that are associated with this particular topic area that I called out. When we think about adaptation strategies for sea level rise, there's an awful lot in this area that needs to be moved forward. There's been a lot of effort in New York after Superstorm Sandy to raise structures. That's feasible for smaller structures like housing, for example. When we think of raising some larger structures, that's not necessarily going to be the solution. We have to think about protecting tunnels. Some of the subway systems in New York after Hurricane Sandy are still not fully recovered from the flooding that happened. So critical infrastructure systems that exist underground, we need to think of new strategies for protecting them. And of course, there's a lot of discussion about tide and storm surge barriers, and we have colleagues in Europe that already have a great deal of experience in this area that could lend expertise and knowledge that we also need. And finally, thinking about achieving emissions reduction, geothermal energy is one avenue that I think offers a lot of promise. We've been, I think, a little bit slower in the US to move in this area than some of our colleagues in Europe. Wind and hydropower, another options which have which need geotechnical expertise to move forward and design. Natural gas, which, as we know, has both opportunities and challenges associated with it. When we think, for example, of induced seismicity as a result of some of the fracking activities that are going on, that would be a challenge associated with further extraction of shale gas, for example. And of course, there are many geotechnical and geoenvironmental challenges associated with CO2 sequestration and storage. So meshing together the type of climate change impacts that we think are going to happen with some of the geotechnical expertise and geoenvironmental knowledge that we have as a community, there's a lot for us to think about in this particular area, not just as researchers, as practicing professionals, and as educators of the next generation, because I would argue that we don't discuss enough in our classrooms, if we discuss at all, many of these important challenges. So I'm now going to move on to an adaptation case study to give you some idea of the work that I've been engaged in that didn't start off as a specific project to mitigate the impacts of climate change, but has sort of evolved along the way into a project that could address some of the challenges we face, particularly in New York City. So these are the projections for New York City. So this is going to an even more granular scale. They were developed by quite a few colleagues of mine at Columbia University, located in the International Research Institute for Climate and Society, and also NASA Goddard, which is affiliated with Columbia University. The top two graphs show changes in temperature and precipitation for the last century in New York that are actually based on measured data. And you can see, particularly for the changes in temperature, there appears to be an upward trend. Now, we can't attribute all of this to climate change. In fact, it's hard to know how much of this to attribute to climate change and how much of this to attribute to the increased imperviousness in our city and the reduction of vegetation, which is going to lead to increases in temperature anyway because of reductions in evapotranspiration. But on the right, we see a trend, maybe it's less convincing, of increased precipitation in the city. One of my students has actually taken all of the rain gauge data that exists in the city for the last 50 years and looked at this trend with some statistical analysis. And we do think that we are seeing increased precipitation, we're seeing increased intensity of storms, and we're seeing a shift of the intensity of storms further into the hurricane season in New York. So we're convinced, although that line might not look so convincing on that graph, that we are seeing an increase in precipitation. So if you add that to the projected climate change models for New York City, and we look at an average scenario as opposed to an extreme scenario, it does look like towards the end of the century, if these projections hold out, we're going to see very significant temperature changes in the city, to the point where the number of degrees where we experience, the number of days where we experience over 90 degrees during the summer may be the majority as opposed to the minority of days. And then with respect to precipitation, we're also going to see an increase of a couple of percent towards the end of the century. I'm not going to talk about the sea level rise and the other changes that we're going to experience, because I'm going to focus on how we might adapt to changing temperatures in the city and changes in the precipitation that we're experiencing. So this actually shows what is currently happening in the city at a baseline scenario, if you may. So the left-hand side, left-hand photograph is flooding that was experienced along one of the major roadways on Manhattan. This wasn't during Irene or Sandy. This was just during a severe storm that happened in 2014. So it was a severe weather event. But we regularly see flooding in New York City. And with increased precipitation and increased intensity of those precipitation events, the flooding that we're experiencing is only going to increase. And of course, it's hugely disruptive to the lives of the people that live in the city. But it's also an issue for our infrastructure systems, and in particular, our underground infrastructure systems. On the right-hand side, you see a map of surface temperatures for the city. You can probably orient yourself. The redder dots are the higher temperature areas in the city. And this is demonstrating the urban heat island effects that the city experiences. So the city experiences higher temperatures, particularly during the summertime, than the surrounding suburban environments. And the red dots show you, the red areas show you where those higher temperatures are more intense. And what you can see, besides the waterways that wrap around Manhattan, the Hudson River and the East River, is a nice rectangle in the middle of the city that appears to be cool, and that's Central Park. All right, so the research that I've been engaged in has been looking at vegetation as an adaptation strategy, both to soak up rainfall that falls in the city, so reduce the incidence of flooding, but also to increase the evapotranspiration that we have in our city environment, which is going to reduce the urban heat island impacts. And just as a sidebar, what happens when we have urban heat island impacts and the temperature in the city rises above levels that are comfortable for the inhabitants of the city is that our energy usage goes up considerably. And as our energy usage goes up, if we're not relying on clean energy, so does our fossil fuel consumption, so do greenhouse gas emissions. So it's a vicious circle when we start to think that climate change impacts are causing us to use more energy, which is causing greater climate change impacts. So this figure here is from the Manhattan Project. I don't know how many people are familiar with it, but the top is a rendering of what Manhattan might have looked like pre-development. So you can see it's a little bit of a different shape to the Manhattan now, which is on the figure below, because of landfilling that's gone on to extend the footprint of the city. But it's also covered in vegetation. And there's a stark difference between the pre-development landscape of New York and the post-development landscape of New York. And what is staggering to me when I contrast these two is how much impact our species has actually had on this particular planet. And it's hard when you contrast these two not to imagine that some of the impacts that we're feeling with respect to climate change are caused by mankind. But what we have done in developing many of our cities like New York is we have increased imperviousness, which is why we have flooding problems in New York when it rains, and we have decreased vegetation. So New York City has embarked on a pretty aggressive program to reintroduce vegetation back into our city landscape through engineered green infrastructure. And the idea of the engineered green infrastructure is to restore the hydrological regime to the pre-development scenario. And in doing so, you're going to allow the rainfall in the city to soak into the subsurface, so you're going to reduce flooding, and you're going to increase evapotranspiration, so you're going to induce cooling. The plan was instigated not to think about adaptation to climate change impacts, but actually to meet the Clean Water Act. New York City has a combined sewer overflow problem. It was in violation of the EPA Clean Water Act. The city decided that a green infrastructure program was much more cost-effective and would produce co-benefits that a gray infrastructure program, which would mean building underground detention systems, increasing the capacity of the subsurface sewer network system, was a better idea. So they have a 20-year implementation plan. It's going to be an estimated cost of more than a couple of $2 billion. It's primarily designed to capture rainfall, to stop the rainfall going into the combined sewer system, and in doing so, stop combined sewer overflow events, thereby cleaning up the city's waterways. But it has a lot of benefits when it comes to thinking about climate resilience and climate adaptation. So more recently, the city, through its Sustainability and Resilience Office and the Environmental Protection Agency, have been quite interested in how far this type of program might go in reducing climate change impacts that are related to increased precipitation and increased temperature. So I've got a slide here that shows some of the example green infrastructure strategies that are going into the landscape of New York. On the top left, that's a green roof. That's actually on a Columbia University building. Columbia University has installed 7 green roofs of this kind, and I'll explain what kind it is in a minute. On the bottom left-hand side, that's a green street. Both the green roof and the green street are vegetation strategies that just capture the rainfall that land on their particular area. In the middle, we have street trees and vine canopies. Street trees already exist in New York. Recently, under Mayor Bloomberg, they've increased the number of street trees in our city by 1 million. We have a large street canopy in the summer. And vine canopies are something which exist in small pockets across the city, but there's quite an opportunity to insert more vine canopies into our city, I think, both horizontally and vertically. We have a lot of vertical surface in New York City that could be greened. So the street trees and the vine canopies capture rainfall by interception and stem flow, and they channel the rainfall into pits that hold the roots of the trees or the vines. So they're a little bit more complicated when it comes to, for example, rainfall capture that might reduce flooding. And on the right, we have what the Department of Environmental Protection refers to as right-of-way bioswales. They're right-of-way because they're on the public right-of-way. Nobody's quite sure why they're called bioswales. In particular, the public is not quite sure why they're called bioswales. So they're moving towards calling these rain gardens. These actually extract water from an area that's larger than themselves. We estimate about 100 times their area. And the top and the bottom of these pictures of bioswales, you'll just see that they have different inlet designs. But all of these strategies rely on vegetation to soak up rainfall. And the vegetation also provides important evapotranspiration benefits that can cool at least the local air temperatures, we believe. So my research group and collaborators, which include the Parks Department, the Department of Environmental Protection, Geosyntec, and a number of community groups, have been studying the performance of all of these green infrastructure types in New York City. I'm just going to go over the performance performance metrics for some of the green roofs that we've been studying in the interests of time. And I'm going to focus on the extensive green roofs, which is on the right-hand side picture here. And this is actually a Columbia University graduate student residence. It's located at Amsterdam and West 118th. The extensive green roof systems differ from the intensive green roof systems. They're actually made of an engineered soil, which is lightweight, and they're planted with sedum, which is a desert succulent, because it's pretty harsh on a rooftop. You get massive temperature swings, diurnal from day to night. Because you have a very thin growing media, you need plants that can adapt to such conditions. The reason that they're of interest to myself and other folks studying green infrastructure is that they can be retrofit on existing building stock. The intensive green roofs are much thicker engineered soil depths. You can have a much wider variety of plant types. Humans can inhabit the intensive green roofs, so they can actually be rooftop parks. But you generally have to design a building to have the structural capacity to support an intensive green roof. So as a climate adaptation strategy, it's probably not so interesting unless you're thinking of designing a city from scratch. So the extensive green roofs can be inserted into your existing urban fabric. I've got a cross-section here through a layer of extensive green roof, and I'm going to try and persuade you that this looks like a landfill cover, and that geoenvironmental engineers should get much more heavily involved in this type of technology. So if we look at the layers of the extensive green roof from the base upwards, we have a drainage layer, as we would in a landfill cover. We have a retention fleece, which we might not in a landfill cover because we have a thicker soil depth in a landfill cover. But the idea of the retention fleece is to try and retain as much moisture as possible in the green roof cross-section so that the plants remain healthy throughout as much of the growing season as possible. And then we have a growing media, and the growing media is engineered soil. And the engineered soils right now tend to be a mixture of organics and inorganics. And the inorganics are often things like expanded shale, which in itself is energy intensive to produce. So if we look at a life cycle analysis for this technology through the lens that Professor Reddy provided, we might not actually think that it's a very environmentally sound technology from the energy perspective. So there are opportunities to rethink what this growing media might be. And on the top, you have the sedum vegetation. So predominantly the drainage through a cross-section of an extensive green roof is a vertical drainage through the layers of vegetation and growing media and the retention fleece, and then horizontal drainage through the drainage layer itself. So it's a sort of a semi-two-dimensional drainage problem. So the common extensive green roof types that we've been studying are the complete system. So that would be when you actually build the green roof on top of a roof. So you bring all of the geotechnical layers to the top of your roof and you construct the green roof in situ. The tray system, where you can assemble the layers of the green roof in a tray and you can bring the tray to the rooftop. This is a little bit more flexible because you can reorganize the trays as you like over time. You can even remove them if you decide that it's not a technology that you want to continue to support. And then the system that Columbia University has gone with, which is the pre-cultivated vegetated mat. And this is assembled off-site, and it comes on site like a carpet, and you literally like roll the green roof out in sections on a carpet. This is the thinnest and most lightweight of these technologies. It's also the cheapest of the technologies, unless, as some schools have done in New York City, you get your students to construct the tray systems, because then you save on labor costs. So they end up being the cheapest system. But in general, it goes the thickest, heaviest system from the top, the complete system, to the thinnest, lightest system on the bottom, with the tray being intermediate. So Columbia University has a green roof network. It involves very many researchers and even more students, because it can be quite labor intensive operating a field program, which is basically what this is. We have 7 full-scale green roofs that are instrumented. We have a couple of pilot-scale test boxes on roofs around the campus, because facilities has yet to discover that we're doing work on a roof. We have a large suite of data collection instruments, some of which we've been able to purchase off the shelf, many of which we've had to design ourselves. We measure the runoff. The difference between the precipitation and runoff tells us of the capacity of these green roofs to help us absorb rainfall and then reduce flooding impacts in the city now and into the future. We measure the evapotranspiration because we're interested in their benefits when it comes to urban heat island, particularly into the future as we expect higher temperatures in the city. We have a lot of MET stations. We're measuring the microclimate on these roofs. We measure CO2 sequestration. I'll produce one graph on that. And we're interested in air quality benefits as a co-benefit, so we measure PM 2.5. These roofs have been instrumented for over 8 years right now, and we have, I would say, well over 100 gigabytes of data that's been collected on their performance. I'm just going to talk a little bit about 4 of the green roofs. They're highlighted in green here. 2 of them are on Columbia University buildings. They're the MAT system. Columbia went for the cheapest, most lightweight system available. One of them is on the Con Edison Learning Center. That's a tray system, and one of them is on the United States Post Office Morgan General Mail facility. That's a complete system. It was until a few years ago the largest green roof in New York City, but the Javits Center green roof has overtaken it as the biggest player in town. 3 of the roofs are on Manhattan, and 1 is in Queens. So these are some pictures of the roofs. The top 2 are the ones on the Columbia University facilities. One's on a brownstone. The other I've already shown you is on Columbia residence. The bottom left-hand corner is the Con Edison roof, the tray system. You can probably make out the trays. And then the picture on the bottom right, I love. It's the U.S. Postal Facility roof, and you can see the Empire State Building in the back here. So we've been quite imaginative. We've called the roof that's located at West 115th, W115. We've called the one that's located at West 118th in Amsterdam, W118. Con Ed, we call Con Ed, and USPS, we call USPS. I'll try and remind you of the roof types as we just quickly go through some of their performance. Okay, so these are what we call characteristic runoff equations. We have a linear scale vertically and a log scale horizontally. We have precipitation on the horizontal scale and runoff from the roof on the vertical scale. The black line would be if the precipitation were the runoff. So the fact that all of the data lie below the black line tell you that the roofs are retaining water, and that's exactly what we would want them to do as a climate adaptation strategy that could help reduce flooding. This is a fairly simple model, runoff versus rainfall. It captures 90% of the behavior. We have models that are much more complicated. We can take into account temperature, relative humidity, dry weather periods between storms, and we can actually do a much better prediction. But I'm just going to stick with the simple model for the purposes of this presentation, because I think the conclusions are pretty much the same. For those of you that work with HELP, for landfill cover design, we've tried to predict this behavior with HELP. Hasn't worked. For those of you that do groundwater flow and contaminant transport, we've tried to predict this behavior with HYDROS, which does unsaturated flow and transport. It hasn't worked. And for those of you in stormwater management, we tried with SWIM, which is a stormwater management model. It hasn't worked. In my opinion, the evapotranspiration in any of these models is not well captured, and I think it's much more complicated than many of the standard models that are out there, including the ASCE RET model. So that's an area of research that I think we are going to need to understand a lot better, particularly given projected temperature changes. I've put this data up here. It's historic rainfall data from 40 years of information that was obtained from the Central Park Met Station. It's metered out by month, and these are box plots with the squares at the square area showing the mean in the middle, and then the plus or minus 25 percentile on either side. I put this here to actually highlight the fact that although we could say that we have on average 1.2 meters of rainfall per year in New York City and around about 95 events per year, there's climate variability year by year. So we can see quite a difference in precipitation and the number of events that we experience month by month in New York City that has got nothing to do with anthropogenic climate change. It's just got to do with climate variability. And I'm going to say that our profession and many others does face a challenge when it comes to thinking about how to deal with longer term climate impacts, because I don't think we often do enough just to think about year-to-year climate variability. And I think if we had that type of approach already embedded in many of our models, it would be a smaller step to start thinking about larger variability on larger timescales. All right, so why do I think that's important? The data that we collected for the green roofs was over a certain period of time. I think the curves that I showed you was collected over a period of several years. And before we make any projections about what that means to their performance, we really need to compare the climate that was experienced during that time period with the climate that we might be experiencing on average. It's possible that the years under which I did the measurements were particularly wet years. My data would be skewed one way. Perhaps they were particularly dry years. My data would be skewed another way. So making projections on a data set of a couple of years, I think is not going to give you the robust trends that you need to really make decisions in this particular area. So what I'm showing you here with the gray bars are the average values for numbers of events, frequency of events, et cetera, for the 40 years of data versus the data that were collected on the roof. And you can see in some cases that the climate that was experienced on the roof is quite different to the average climate. So we have to take that into account with our model projections. Just as a sidebar, it's been really interesting understanding, or not understanding, let me be upfront, not understanding the spatial climate variability that happens within a dense urban environment. If we just use the rainfall that we measured on the Central Park Met Station to make these projections, we'd be way off for some of the roofs. In particular, the brownstone, which has a much taller building next to it, and rain shadowing means that the precipitation that falls on that building is actually reduced significantly. So that's another complexity to add to this whole challenge. So we ran the characteristic runoff equations through 40 years of individual storm data. We metered the storms out 6 hours by 6 hours. It turns out there isn't a standard way to do that, which was quite surprising. So we decided that a dry period of 6 hours was required to separate storms. So if you had rainfall and an hour later you had more rainfall, we considered that to be the same storm. So you needed a 6-hour dry weather period. But these are the predictions that we came up with for how the different green roof systems, the two vegetated mats, which are W1 W115 and W118, the TRACE system, Con Edison, and the complete system, USPS. How much rainfall they would retain for different storm sizes. And this is the type of graph which we would use to actually figure out design principles for green roofs when it comes to dealing with climate change impacts that are associated with flooding. You can see some quite interesting behavior that I don't have time to get into here, but the complete system for the small storms, which happen most frequently in New York City, retains almost 100% of the rainfall. But its performance compared to the TRACE system reduces as the storms get larger. So how you want to use this for design is really going to depend on what your design goals are. We can put it more simply. We just want to go with annual values. These are box plots that say that the green roofs retain between 40 and 60% of annual precipitation, depending on what technology you have. And these are the design curves that we have come up with if you actually want to look at duration and return period of storms in the city. These durations and time periods are based on historical data, but if we have information about local climate change impacts on precipitation, we could easily change this design curve to say this is what you might expect the green roofs to retain 50 years from now, depending on what type of storms you were expecting. And we actually have these type of design curves, not just for the green roofs. We have some for the street trees, for the vines. We're developing them for the right-of-way bioswales. I've just got a couple of slides where I'm going to talk about the evapotranspiration before I move on to some generalizations about this work. The evapotranspiration is quite interesting. Measuring it, understanding it, and then linking it to urban heat island effects, I think is still an area that requires a lot more research. On the top left-hand side here, though, I have an image that was taken from an infrared camera to illustrate how some of these green infrastructure interventions can dramatically reduce surface temperatures. So what you're seeing on the top left-hand image to the right is a road base where we've got actually quite high temperatures, averages of 107 degrees. Then you move towards the curb where the temperature is even higher. And then that purpley area is a right-of-way bioswale where we're seeing the surface temperatures are quite reduced. So there's quite dramatic surface temperatures associated with these vegetation interventions. The question that we still have as a research group is what does that mean to the air temperatures? Because the surface temperature is not the air temperature. So we're embarking on trying to understand what that means to the local air temperatures, but more generally, what would that mean to the city air temperature overall? But we've been measuring evapotranspiration with this dynamic chamber system. There's a photograph on the bottom left. We've been able to see diurnal changes in evapotranspiration and also seasonal changes in evapotranspiration. As I mentioned earlier, we are not personally finding good agreement between the models used to predict evapotranspiration and the measurements that we're getting in the field. So again, we've moved on to develop our own model, which is really based on empirical observations. And in the bottom right-hand side is the summary of all of the data that we have to date. The top two diagrams show measurements on the 118 and the USPS roof. And so we basically created a contour map that enables an estimation of evapotranspiration based on air temperature and relative humidity. But again, linking this to linking this to changes in general city temperature that might reduce urban heat island is a step that we are still needing to take. So I just want to summary results to date. just from the Green Roof program. We know that they can help mitigate the impacts of increased precipitation. We think at least they can absorb 40% of the precipitation. And with active systems, I think that they can do even better. And I have a quick slide on an active system in a minute or two. We know they can reduce surface temperatures, and we're still trying to figure out what that means for impacting the urban heat island in a positive way. And what I have here is a graph that shows that they can also sequester CO2, but really not enough to write home about. But they have that additional benefit as a mitigation strategy. If we think of adaptation and mitigation as two separate entities. All right, so what are some of the challenges that are associated with this particular adaptation strategy? You want to think about the scale of implementation that would be needed to really make a difference in the city. Right now, the city is inserting thousands and thousands of these interventions into the right-of-way, and it's still really not going to be enough. So we really need to think about how to get these interventions onto private land. So we need to think about public-private partnerships. And we may need to think of new zoning and policy options. If we have vacant land, maybe instead of giving it over to redevelopment for new condos, we need to start thinking about giving it over to these type of greening strategies if we're serious about climate adaptation. The siting requirements, particularly from the geotechnical perspective, have ended up being fairly challenging. Each one of the right-of-way bioswales that goes in has to have its own individual geotechnical testing program, looking for depth to bedrock and looking for the infiltration capacity of the subsurface soils, because they're not going to perform if they can't drain properly. So the right-of-way bioswales, each of them is now costing the city $55,000. Yeah, I feel the same way. And this is the issue with geotechnical. So I feel like we need to think of better ways or cheaper ways or non-invasive ways of subsurface characterization. If this adaptation strategy is even really going to be economically feasible. The maintenance requirements are also becoming quite challenging for the city. The prior DEP commissioner told me once that she'd inherited thousands and thousands of parks and she had no idea how she was supposed to maintain those. We need an increased workforce to do this, or we need to get citizens engaged in stewardship programs, or we need to think about some low-cost monitoring technology that will let the city know when they need to maintain these so they can at least be efficient about that. And we've been looking at resistivity measurements, and we've developed a citizen app too to try and address this particular challenge. So it's not just the cost, it's the maintenance. We're not certain about the long-term performance, so that's why I think it is an adaptation strategy that needs adaptation itself. The public stakeholder acceptance has been a little bit spotty. I've got one slide on this. I don't know. This was an article that appeared in the New York Times maybe a couple of weeks ago. This is a resident from Queens who lives next door to a right-of-way bioswale, and she's not very happy about it. So she's managed to get local politicians and fellow residents to also lodge protests about this green infrastructure strategy. She's complaining about the waste that it attracts, so you can see that garbage is being thrown in the pit. Other residents are worried about losing car parking spaces. What does it mean? Can I park in front of it? The city's been quite aggressive at planting natives. Turns out most people don't like grasses. They think they're messy. It actually turns out from a research perspective, they don't do much for evapotranspiration, so that's a win-win. We can take them out. But there are multiple things that the public who is receiving this infrastructure next to their homes are not really understanding, and that's a big issue. And it's a big issue that is not the public's problem at all. It's the problem of the folks that are engaged in rolling out programs like this. Before I sort of move to wrap up, I've got a couple of things that we're working on in this area that I just want to introduce. We've been working with Geosyntec and OptiRC on trying to design systems that respond to storm tracking itself. So it's an Internet of IoT technology. For some of the systems, we collect the rain in rain barrels. We use it to irrigate the green roofs. But we can use weather forecasting and smart control to empty the rain barrels before the storm comes through. So we found that that's actually increasing the capacity of the green roofs to mitigate impacts of flooding in the city. We've also been working with new growing media to try and address the fact that the current growing media are using materials like expanded shales that are not necessarily environmentally friendly. So we've been looking at different recycled materials as an alternative. And some of the recycled materials we're looking at, like drywall, seem quite promising. Others like roof shingles, plants don't really seem to be happy with the roof shingles. But there's an opportunity here, I think, for those of us in geoenvironmental engineering to think through the design of these systems in a way that could make them a little bit more sustainable. We've also been looking at developing methods of engaging stakeholders. So this is a GIS tool that we developed where we ask stakeholders not only to think about the use of green infrastructure to reduce flooding and stormwater impacts, but are there other things they care about? Maybe they care about biodiversity, maybe they care about air quality. And taking that into account, we can possibly site the green infrastructure in ways that provides co-benefits to communities and makes the green infrastructure something that they perhaps appreciate a bit more. So I'm just going to wrap up talking more generally about this approach. So I think of the green infrastructure as an adaptation approach that is moving us away from a centralized system to a more decentralized system. So a neighborhood infrastructure intervention. The advantage of a decentralized system is that you can add to it, and it's flexible. And if you've targeted an area where you thought there were going to be impacts and it turns out that there's another area which is more in need, you can sort of move your strategy spatially. So I think it offers a lot of flexibility when we think about adaptation to climate change. Building a massive infrastructure, for example, a big underground detention basin, might not offer us because we're sort of stuck with that particular design at the time that we design it. So the distributed infrastructure paradigm is taking off in other areas where people are thinking about adaptation to climate change. On this slide, I've got examples like solar panels. These are on individual homes at the top, but there are also solar gardens that communities are developing. These are not also enabling us to reduce emissions, but they're providing some sort of resilience if centralized power systems happen to be at risk due to climate change. We also have rainwater harvesting as an example of a decentralized system in zones of the states where it's actually allowable. We've got some buildings in New York City that have installed their own wastewater treatment plants in the basement. So they've sort of stopped relying to the extent that they can on centralized treatment plants. And in New York City and in other cities, we've also got growing interest in urban farming, which comes back to the issue that how are we going to feed an expanding population on our planet under some of the climate scenarios that we're seeing being projected into the mid towards the end of this century. So that's another way of thinking about food security in the face of climate change. So this is actually quite a shift from the way that we as engineers normally think of designing systems. We don't normally think of designing a system that has thousands and thousands of components and expecting that system to deliver the same performance as a more centralized system. So we're going to need a change in approach if this is an adaptation strategy that we think actually has promise. And I would say at this point in time, we're probably not able to say that it would be the adaptation strategy, but it may be one in a portfolio of adaptation strategies that we want to think about. So what are the changes in approach? If we have a system that has many, many components, in the case of the green infrastructure system, thousands and thousands of components, how are we going to define performance? If we're going to put a factor of safety on that, do we put a factor of safety on every component? Maybe a factor of safety of 2? Or do we double the number of components and get our factor of safety? I don't think we have any answers to the design performance of distributed systems like that. And how do we quantify the performance of a system with thousands and thousands of components? My research group and others have been quantifying the performance of the individual components, and I would argue we've made some headway, but that doesn't add up to the performance of the thousands and thousands of components. So I think that's still a pretty large design challenge. How do we monitor the performance? That's also a big deal. And how do we maintain the performance? So I think these are all challenges if we move into this type of approach that remain on the table. I put a cloud here that said big data because I really think if we start thinking about these distributed systems and we are able to develop affordable monitoring systems that can look at the performance of every component, we can probably move away from trying to figure out a deterministic performance using equations to actually using methods like machine learning to understand the performance. So I think this is something that as engineers we need to start embracing. The infrastructure systems, many of these, including the solar panels on roofs, the rainwater harvesting systems, the green infrastructure, they interface with the public. I don't think we're used to designing infrastructure systems that interface with the public. And I think that's going to be giving us, opportunities to rethink how we can improve public understanding of some of these systems. But it's also going to leave some of these systems in a gray area of responsibility. So who has responsibility for maintaining these systems if they're in the public right-of-way? What we're seeing with the green infrastructure in the public right-of-way is they do not perform as we've designed if the public actually decides to trash them, to pull the plants out, to change the plants in some cases because they don't like the ones that are planted. So, so there's somewhat of a public responsibility for the maintenance of these systems as well, and I think that's foreign to us as well. And then we have scale issues. It's not clear at what scale some of these infrastructure systems work. Is it a solar panel on a house? Is it a community solar garden? Where's the knee of the curve for that? There's going to be trade-offs between different infrastructure systems. Do I put a solar panel or a green roof on a rooftop? We don't really know what that trade-off is going to be. And there's equity issues too. I'm going to use the solar panels as an example. There are many communities in the States that are in regions where solar panels make sense, who can afford to put solar panels on the roofs of their houses. They can reduce their reliance on the on the centralized power distribution system. They can often sell the energy back to the grid, and so they have economic benefits as well. But for the communities that can't afford this, the grid still has to be maintained. And so the cost of maintaining that grid, if we're not careful, may actually shift to the communities that cannot afford to at least take some of their reliance off the grid. So it's also not clear if we move in this direction how we deal with some of these equity issues. I've got some examples of distributed systems in the geotechnical and geo-environmental area just before I wrap up. We have the green infrastructure example. I hope I've convinced you that this is a geo-environmental problem, not just in the role of some of our colleagues in hydrology. I think we have things to offer here. Geothermal systems, energy piles, and energy walls are also examples of distributed systems that I think fall under our particular purview. Localized flood protection too. There's been a real interesting move in New York City after Hurricane Sandy in real estate development, particularly high-end real estate development. Those that can afford it are now constructing condominiums or condos which have waterproof basements. They have vault systems, which is where the services come into the buildings, that are waterproof. They have the capacity to build their own little stormwater barriers around the building, and they have backup systems for water supply and energy supply. So when we heard about the person that said, I believe in climate change, but it won't impact me, they exist. Because they have the financial capacity to buffer themselves to the extent that they can to some of the experiences that the rest of the public don't. So we are actually seeing localized flood protection developing, although the photograph that I have here is an idea for how we might think of protecting some of our underground tunnel systems. That I think of it as a blow-up cork. And rainwater storage is another example of where underground rainwater storage, where we can have localized systems that are actually relevant to the design and research capacities that we have in our geotechnical community. So this is my final slide. All right, so what are the needs in future practice, research, and training? I think that we all need to be aware of what our colleagues in climate science are doing. I think we need to understand to the extent possible how they generate their climate change predictions, what models they're using, and what assumptions they're using. I'm going to stick my neck out here and say that I think that all engineering undergraduates should have some training in this area at this point in time. Because if we don't understand something of what our colleagues in climate science are doing, we cannot tell them what we need out of these particular models. And we can't have a two-way conversation where we actually explain to them the parameters that we use in our design and research, and see if they can, through their modeling exercises, give us some indication of how those parameters might be changing over time. I think we need to develop a better understanding of the impact on climate change on geotechnical engineering structures and practices. I was really impressed by a lot of the work that we had presented today. But one thing that struck me was, as a community, we actually haven't come together and thought about this collaboratively and thought about unified approaches to this to the extent that they're actually possible. I was particularly struck by the work that was being done on the dam and levee safety, and it strikes me that our colleagues in hydrology and our colleagues that look at ecosystem services have been producing global maps of vulnerability and crisis, and how is this going to change as we evolve into this century. And I feel that we haven't done that. And I think that we could start thinking about vulnerability maps for dams and levees as they exist now, as we know to the best extent. And then we could look at how some of the climate change impacts might increase that vulnerability. So we could start actually looking at areas where we need to target resources in the very near future. And I know that's an enormous challenge, but unless we start to do this, we're still really going to be looking at individual projects, individual geotechnical needs. Maybe we're not going to be efficient with the resources that we have. And if we have something like that, we could understand our progress to reducing vulnerability, and we could develop ways in which we could actually potentially quantify that so that we could see that we're moving in the right direction. This has been mentioned several times today. We need to learn how to integrate engineering, ecosystem services, and social strategies. There isn't an engineering solution to this. Engineering is a piece of the solution. It's an important piece, but there are other pieces that need to come to the table. For certain, we need to engage stakeholders. Because if we go back to think about the picture where we had Manhattan pre-development and current Manhattan, to think that some of the impacts of climate change are not caused by mankind does seem to be quite naive. Thank you.